Okay, well, welcome to 6950. As I said, we're going to start with something on assignment number 7. And in Slack, I grabbed 2 volunteers of people who have not yet spoken. Just as a reminder, I'm trying to get everybody an opportunity to talk about their assignment, even for a few minutes. So on Monday, we'll have 3 people left, and we'll do assignment 8, present it, and that'll all be done. So for today, Atea and Jingyao are the 2 people who I think I've tapped. And I'm just trying to figure out whether or not I have access to your assignments or not, because I'd love to see what you actually did. Let's see here. I just need to look up some GitHub identities so I can share the right page. Oh, that'll work. Yes. Okay. Atea, yours is good. And Jinyao, you uploaded something. Have you shared your CMSC6950 assignments repo with me? Oh, he's typing. Well, here, let me, I'll invite the 2 of you to turn on your microphones and cameras so we can actually see you, if you can. I will share a screen. I will share.
Hello, Professor.
Hello there.
Hello, sir.
Hello there.
Why it cannot?
Well, I don't know why not. So there's GitHub, Viola 233.
Yeah. I do. That is not private. Sorry.
It's okay. We'll figure this out. So there's Atea's, and we can do. So I have your right GitHub identity, right?
Yeah.
Okay. Repositories. It must be a private repository.
But the repository when I install it is not it's not private one, so.
Okay. Well, that's fine. You know what, Jinyao, can you share your screen? Maybe that's the easiest way. We'll start with you, and then we'll flip over to Atea later on.
I didn't finish all my project 7, so.
No, we don't. We just need. Did you do the last part of assignment 7?
Nope. I didn't do that part, so that's the problem. I should be volunteer today, but I didn't finish it, so maybe next time.
Okay.
Do we still have next time?
Well, there's one more time, but we'll figure it out. Okay. No worries. If you're not ready, I'll flip on to Atea. You're there? I see you on the screen. Fantastic. I happen to have yours in front of me. Thanks very much. I just wanted to talk about. I wanted to see this, and then talk like it's a very short take up because it's only one little question. But I needed someone's code to discuss. So I will ask you, Atea, what does this code do? What is this loop upon a loop upon a loop? What's it doing?
So the question asked me to create 2 matrices, which name is A and B, and then multiply with each other and store the result in a sealed matrix.
Okay, so you're doing a matrix multiplication, right? So you're multiplying all the rows and all the columns together. So my only question about how you've done it is, what happens if A and B were not 100 by 100? What if they were 10 by 10?
I choose 100 by 100, and also I can change the number.
But what if you wanted to change the number? What if you wanted the matrix to be a 10 by 10 matrix?
Okay, so I think I had to put, for example, two variables instead of number, and after that, I had to put my number in that variable instead of putting my number in my function.
Oh, okay, so let me do this. Let me just go to a brand new empty notebook, and we're just going to play with your code for a second. So there's your algorithm, right? And I know we need import as NP, right? And to be able to use your algorithm, I will just go back to, here we go. Here's what you did. And this is good. I just needed something to work with as an example. Let's just see if your code actually works as expected. Okay, so it's taking 560 milliseconds. Okay, so here's something that's going on. When you're timing it, we want to time how long this function takes to run, which is not quite the same as how long this function takes to run. So if it was me, and I'm not just speaking to you, I'm speaking to everybody, what I would do is I would pull that initialization out of the routine, because you don't really care about how long it takes to create the arrays. What you care about is how long it takes to multiply them together. That's one. The second thing is the code should work for that as well. But it's a bit weird, right? So if I do my matrix multiply of A times B, I'm getting an array which is 100 by 100. And of course, the 10 by 10 matrix, when you multiply by another 10 by 10 matrix, should be 10 by 10. So what you need is you need some way of figuring out how big an array is. So do you know in NumPy a way of taking an array and figuring out its dimensions?
Yes.
How do you do that? I can remind you that you would have already done that earlier in the assignment. Does looking at
type command?
No, not a type. A type would say what it is. Oh, we're missing the question. You're not quite done assignment 7.
Yes.
Okay, so you still have a bit more to do on assignment 7. Right here. See what you're doing here? Shape. So shape is how you figure out how big an array is. So if you say a.shape, it's a 10 by 10 array, right? And if you make it 100 by 100, right, then shape is a 100 by 100. So what you can do is in your program, you can say, well, my array is a.shape. And then m is a m by n. And then your loops, right, can really be, well, they're always square. Right? So what you can do is you can actually look at the shape of the array and use that information to build it all the way up. So when I do that, it makes the code go a little bit faster because I don't actually have to create that array all the time. Now, in practice, it doesn't really matter because most of the time is taken up with these 3 lines of code. So what we have discovered is to do a matrix multiplication on 100 by 100. We're taking about 600 milliseconds on my computer. And on your computer, when you did it, you took 719 milliseconds, right? Okay, so my question is, what happens when you do this with NumPy? So in this second bit of code, again, I wouldn't normally put this inside the time it, but it's not a big deal. How much faster is NumPy than your matrix? What's the ratio between these 2 numbers?
It's obvious that if I use numpy's dot function, it will be really faster than I just put them in matrix and not using a dot function in numpys.
Right, but what I'm trying to get you to recognize is how much faster is it? Is it twice as fast? Is it 10 times as fast?
It's really faster. When I computed without a dot function, it took 119 milliseconds, but when I use dot function in NumPy's library, it became 71 microseconds.
Right. So I just want you to understand what the units are here, right? 700 microseconds is, you multiply that by 1,000 to get that into microseconds, right? So what would it be? 719,000 microseconds compared to 71. So there's a factor of what? Is it 10,000? Am I reading that correctly? Yeah, it's like a factor of 10,000 between those two things. Right, it'd be 1,000 if it went from, yeah, it's 10,000 times faster. So this is why when we're doing stuff in Python, even though we might write a formula like this, we very rarely actually let the code be like this. We want to try and find some lower level function or something that's in a compiled language, because you get a 10,000 times speed up for a 100 by 100 matrix. But I wanted to continue this along a little bit. I wanted to ask, okay, well, if that's how long it took 100 by 100, how long would it take 1,000 by 1,000 and a 10,000 by 10,000? And I can see from your data, it took 71 microseconds, 9 milliseconds, 5 seconds. Okay, can you see how this is a power law? Do you know what a power law is? A power law is where something depends upon a power of a number. So the time taken is not proportional to the size of the array. It's not like it takes 71 microseconds, and if you go from 100 to 1,000, it takes 10 times as long. If you go from 71 microseconds to 9 microseconds, it's taking a big jump, right? It's an order of magnitude. It's proportional to, well, what I would guess is about 1,000 times slower, right? And the reason is you're multiplying it by 10 by 10 by 10. When you jump from a problem size of 1,000 by 1,000 to 10,000 by 10,000, you don't increase the length of how long the program takes to run by a factor of 10. You increase it by a factor of 1,000. You're going from milliseconds to seconds. And that's because the scaling of this problem is proportional to the cube of the size of the matrix. So we say it's a power law. We say that the time is proportional to n squared, where n is the size of the matrix. So have you done stuff with, like, have you done a computer science course and talked about big O notation? Have you taken a course in algorithms? No, you haven't done algorithms? Okay, so you're not in computer science. You're in a different discipline then. What program are you in?
I'm from computer science.
Have you taken a course in algorithms?
In bachelor.
Well,
It's
yeah,
my first-
in your bachelor's degree, like you took courses in algorithms, right? Searching and sorting and
Yes.
all those kind of things. So did you learn about big O notation or evaluating how fast an algorithm will run? Was that covered in your bachelor's degree? It might not have been. It's just this is
remember.
Okay, so this is for all of you who are going, I don't know what this is talking about. When we talk about an algorithm, okay, we sometimes like use this idea of what's called big O notation. Okay, so big O notation is how fast something grows, and we use it when we're discussing the analysis of an algorithm, right? How fast it is. So we say, and I'll just do this little slide for an example, a constant time algorithm is order 1. It means it doesn't matter what you give it, the amount of time it takes to run is always the same. A linear time function is order n. That means if you double the amount of input, you double the amount of runtime. A quadratic runtime is order n squared. That means if you double the size of the problem, it runs 4 times slower. If you make the problem 10 times bigger, it runs 100 times slower, right? So that's the idea of big O notation. For your problem, what you've discovered by looking at the data of going it from microseconds to milliseconds to seconds is every time you increase this by a factor of 10, you're increasing the runtime by a factor of 1,000. And since 10 times 10 times 10 is 1,000, matrix multiplication is an order n cubed thing. So if you want to figure out how long a program will run, what you can do is you can figure out how long it will run for a certain case, and then you just basically scale it up. It's going to run whatever this time is times 1,000 times 1,000. So my question in the last bit here is, assuming my matrix runs proportional to the cube of n, okay? That is, the amount of time taken is growing by the cube of n. How long would you expect the program 10,000 to run in the original version? And what you did is you tried to actually time it, okay? Which is never going to work, okay? So I'm gonna ask this again. If this algorithm, every time you go from 100 to 1,000 or 1,000 to 10,000, goes up by a factor of 1,000, okay? Microseconds to milliseconds, milliseconds to seconds. In your original program, it took 700 milliseconds. How long do you think this program would take to run if this was 1,000 by 1,000? Goes up by a factor of 1,000. So what's 719 milliseconds times 1,000? It's just units, right? A millisecond, there's 1,000 milliseconds in a second. So if you multiply by 1,000 milliseconds is just 1 second. So 719 milliseconds is just 719 seconds. Do you understand that?
I think the time taken will be no, I don't. I think
What we've demonstrated is with matrix multiplication, going up by a factor of 10, so 100 to 1,000, increases the runtime by a factor of 1,000. It goes from microseconds to milliseconds, okay? So what I'm saying is, if you go from a problem which is a size 100 to a problem which is size 1,000, you're going to go from 719 milliseconds to something on the order of 700 seconds, which is about 10 minutes long.
Mhm.
Okay. If you were to go from a problem which is 1,000 by 1,000 to 10,000 by 10,000, you'd be talking about 700,000 seconds. Okay, which is about a week. So this program, if you were to let it run, you'd only have to wait 7 days to get the answer. Okay, and this is the point. 7 days versus 5 seconds. Okay, this program, if you were to actually let it run, and you couldn't, yours died because you didn't, yours isn't written, but if you actually tried to run it, I would expect this to take 7 days of your computer churning, but with the right algorithm. So this is just to point out why we use things like NumPy and compiled languages. We don't write algorithms in Python itself. Okay, just stuff on computer science. Okay, so I want to just step back from this assignment, just talk about computer science in general. So you're in computer science. Many of you taking this course are in computer science. Are algorithms and data structures not the bread and butter of what you do? I didn't do a graduate program in computer science, so I only did an undergraduate. I always assumed that you still take courses on that. Am I wrong? And I tell you, you don't have to answer. Maybe someone else wants to answer as well. Do those of you who are doing graduate degrees in computer science, do you think about algorithms and complexity and order of big O notation, or is that not something that a computer science person does? I'm just waiting for a voice to speak up and say something. Yashar says that's fundamental. Okay, I thought it was fundamental. So and not just in computer science, but like in science, right? Okay. Anyways, thanks very much, Tatea. We'll move on to a different subject. For those of you who have not presented yet, I'd really like to have you say something about your assignment 8, so I can give you a nice check mark. But we'll continue on. Okay, so where were we? As you see, I've got a different background. I've moved to a different location with a permanent internet connection because it just was not working for me on Monday at all. And what I'd like to talk about is data storage. Okay, so these are just some notes that I whipped up that I was beginning to go through. And what I wanted to convey, what I wanted to share was the fact that when you're doing scientific processing, you almost always generate data, right? You're either generating either observations like satellite observations or telescope observations or microscopy images, or you're generating data from a model so that you start off with no data, but then on the disk, you start saving larger and larger quantities of data. And the reality is, as we have made our computers go faster and faster, we tend to generate more and more data. Now here's the challenge though. When we talk about things like big data, growth of data in science. Okay, I don't know. I'm trying to find some image. It'll show me some power law, right? That's for data science jobs. No, I don't want to know. I want data volume. Yeah. Okay, here's sort of a typical graph. I don't even know what this is from, but it's one of these graphs. How much data is out there, right? You could think about the amount of data as a function of time. So over the last 15 years, so the entire time that every one of you has sort of been doing your schooling from whatever before high school was through your undergraduate into your graduate degrees, right? You can think about this chart, and the amount of data is increasing by a factor of 5 every 5 years, right? So every 5 years, it's increasing by a factor of 5, right? So we are now talking about data sets on the order of zettabytes or zotobytes? Zettabytes. Zettabytes overall, but that's every data set we got. One of the problems, though, is data storage doesn't grow as fast as computation. So you're familiar with, I said, I'm just looking for a standard graph. Are you familiar with this picture? I'll just show you an example of it, right? If I show you this picture, no, I do not want to see that. Okay, there is a classic picture. If I show you this snapshot, are you familiar with this graph? What this is supposed to tell us? What it does? What does this graph have to do with anything?
This is probably processors, James, for computers.
Yeah.
Sorry.
Yeah. So what it is, this is something called Moore's law, as in Moore from Intel fame. Observed that back in the 70s or the late 60s and 70s, the number of transistors per chip appeared to be doubling about every 18 months. And so for a long time, what we had is CPUs got faster and faster on a time scale of about 1 to 2 years. Every 2 years or so, computers got faster, right? So you know all the things about a supercomputer back in the 80s has as much power as like my cell phone does right now, if you've heard of those kind of things. That's because we've been able to pack more and more transistors into a CPU chip. Now, we're at the level right now where it's difficult to pack any more transistors into a single chip, but we just solved the problem by creating more cores, right? And if you've been familiar with computers and computer lingo, right, these words, duo. You see that word duo and quad? What does duo and quad mean when it comes to buying computers and computer stuff? Number of cores, exactly. So we went from 2-core to 4-core to octo-core. And if you follow computer stuff at all, you will see that like 32-core, 64-core is sort of where the high performance machines are right now. That's actually not impressive. When we talk about graphics processor units, 512, 2048 cores, that's how we're maintaining effectively Moore's law right now. We can't cram any more transistors in there. We're just going to keep on doubling. And we're doubling continually about once every 2 years. And so that means that the amount of computational problems that we solve also are doubling. So in the same way that we looked at matrix multiplication, something which is proportional to in runtime to the cube of how long it takes, if I give you twice as much computing power, I can do a larger and larger computational problem. I can simulate the world with more resolution. I can do more simulations, more Monte Carlo modeling. I can deal with more and more stuff. But there's a problem. And the problem is, if you look at the same sort of graph, which is the graph of storage costs, okay? So if we talk about, I don't even know where we're gonna get this. Okay, so here is one of those graphs, okay, that shows that how much money it costs to store 1 gigabyte of data. Now, I said it depends on your age here and where you're at, but there was a point where having a gigabyte hard drive was like an amazing thing, and it's more amazing depending how old you are, because like when you have when you're used to a 360 kilobyte floppy disk, a gigabyte of hard disk space is a ridiculous amount. And once again, a gigabyte of data today is not too impressive, because if you go when you watch a movie on Netflix or Amazon Prime, you're probably downloading 2 or 3 gigabytes per movie. So you're just not nearly as impressed anymore. Just to give you a sense of where I'm from, my memory of using computers and getting into this is from the late 80s, early 90s. That was sort of my getting into this whole world. And I remember installing software where what you got is you got a stack of floppy disks, and the software came on 8 or 12 or 16 floppy disks. And you put floppy disk 1 in, it buzzed for a while, and it said, please insert disk number 2, and insert disk number 2, and it buzzed for a bit, and repeat, repeat, repeat. So those were only like 1.4 megabytes a piece. The point is, storage has got cheaper. That's true. And this graph I'm showing you is on a semi-log plot. So it's got cheaper as a power law. Okay, so it is getting cheaper and cheaper and cheaper. But the rate at which computation is growing far exceeds the rate at which storage is getting cheaper. And so we actually have this problem where we're able to compute more now than we are ever able to store. Okay, and that's not just in our modeling, that's also in our ability to do experiments. Are you familiar with, let's get some pictures. There we go. That thing. Do you have any idea what that thing is used for, or what that's supposed to represent? And I'm seeing the letters CERN all the way over here. I'll give you another example of what it might be. There's another shot if you've ever followed science. What is this thing? Are you familiar with what this this image is supposed to represent? That's a terrible shot. There we go. That's something that looks pretty sciencey. That's a particle accelerator. Exactly. So that's the Large Hadron Accelerator in CERN. This instrument, right? You're shooting particles around in a circle, making them go very, very, very fast. Those particles go through and interact with these large detectors. Okay, so whether or not it looks like that, or it looks like this, or it looks like this, basically it's a lot of magnets trying to show you what's going on. They generate a lot of data. The reality is we can compute the data, but we have no way of storing the data. There is not enough hard drives to store the data generated from these particle accelerators. So what happens in practice is we actually have computers which watch the data and throw out most of it. And then they only keep the part that be analyzed. Even the part that we can analyze is a ridiculous amount of data. The point being, when you're talking about computational science, not only do you care about how fast your algorithm runs, you care about, and you have to think about, how are you going to store that data? How are you going to access that data? How are you going to post-process that data? Can you save to the disk fast enough to make it work? These are all serious, ongoing issues in computational science. They're part we want to worry about. So that's sort of what's motivating why I'm going to talk about something as low level as input-output, file formats, and data storage, just to start to talk about some of the issues or concerns or ideas that would go along working with it. So we began to lead into it when I got cut off on Monday, this package called PyGrid. So a pure Python gamma ray burst analysis package. It doesn't really matter what the package does. The point is it's collecting images from telescopes, and that particular community has decided that the FITS, Flexible Image Transport System, is an appropriate storage model or data model for storing this kind of data. And you can go off and do a search on Google for a whole bunch of things about it. Here, I just sort of did a search, and here's NASA.gov's primer on it. And this is a data set which its origins date from like the early 80s. Okay, so the earlier versions of FITS is sort of an early 80s sort of format. And you got to remember where we're at in the history of computers. Computers and file formats are indexed by which bytes represent which things. And so the way that the data is set up is these sequences that are 2,880 bytes long, right? Which probably had something to do with the hardware they were using. It was one data block on the tapes they were using. And they would put certain kinds of numbers in there. And the numbers could be integers or floats or what have you. And they build up data. And so the data after this block unit of 2,280 bytes will be arrays of either 8-bit integers, 16-bit integers, 32-bit integers, or 64-bit integers. And there'll be sort of these tables. And what this array storage format allows you to do is basically efficiently save to disk arrays. And one kind of array, of course, is an image. An array, like an image, is just an array of pixels in whatever color bands you want to save it in. So that's a two-dimensional array. But you could have a three-dimensional array, which would be like a movie, a sequence of images over time. And the idea is there are these domain-specific file formats out there which have been designed to use for scientific data. So FITS was one you'd use for astronomy, right? You're not limited to any one particular data storage. In different fields, there's different ones to use. We've actually seen the use of some data storage already. So here's another package that's in the astronomy world. This is called FruitBat. So FruitBat is for estimating redshifts. And so I went and I took a look at the source code and I'm like, well, what kind of data storage does this product use? Well, if you actually take a look at it, it's saving its output in NumPy files, okay? And we looked at this last time. What is a NumPy file? That's just a flat array that's been compressed with gzip and saved bit by bit by bit with a little bit of metadata that says what the binary type is. So in some ways, this NumPy format is really just an equivalent to what this flexible image transport system would have been developed originally. Now, there's extensions to FITS, but if you compare FITS in the 80s to what NumPy is today, they sort of do the same thing. They're responsible for storing efficiently arrays of certain data types on disk. There are other data types that FruitBat uses, including what's called a CSV. Now, a CSV, we looked at these at the beginning of the course, right? What is a CSV? A CSV is a flat file, plain text file format, which is distinguished by the fact, here, I'm going to just show one. I'm going to find a picture. Okay, they look like this, right? So they are typically rows. So every row of a CSV is a record. There are multiple rows in the file. That's why it's using lines, as in plain text lines, to separate them. Even though they're called comma separated values, you don't actually have to use a comma. You can use semicolons, you can use tabs, you can use other symbols that indicate separation of different fields. Within the fields, sometimes what we do is we use quotes to be able to surround spaces, but there's certain things we do with them. CSV files have the advantage that they're fairly easy to read and write. Every programming language has that we modernly use typically has the ability to read a string of text or write a string of text. We as humans have a way of visualizing the data. So if I just give you this file format and I just give you this data just by looking at it, you might be able to recognize that these are what appear to be like Dewey Decimal codes for books. Then you've got some sort of information on an ISBN, so the number of pages or some sort of code, and we can read the symbols. Here we go, the price, Euro 30. Okay, so in this file, we've stored the price of this thing, and we can read out the 3000 or the 2260, 10700 as characters stored on the disk. Okay, what I want to talk about, and I apologize if this is totally obvious, but I don't think it's totally obvious to everybody. Could someone comment on the difference between saving a bunch of data as a NumPy file format versus a CSV file format? And I'll get specific here. So let's import NumPy. Okay, so we have a NumPy thing. Let's create an array. Okay, our A is equal to np.ones 100, 100. Okay, so there's, oh. There, it's a bunch of ones, it's pretty boring. And we know that we have within the, say, file a.np We've got the ability to save. There is also a text format, which is really similar to a CSV file that saves it in this way. And what I want someone to comment on, if you understand the difference between a CSV and a NumPy file, what are we expecting to be the differences in these two file formats? And I'll give you some hints in terms of looking at these things. So there's the same data, binary versus text, and that's exactly right. Okay, so a binary file format is storing each one of these numbers in its binary representation, which means if you want to store the number like 10000000000, you need that many characters. But as a binary representation, you only need as much bytes as to store the precision of that number. Okay, so you can see that in this very naive way, this 100 by 100 file is only 79 kilobytes for this storage format, but it's 245 kilobytes in this storage format, right? Now, there are pros and cons, right? So in the sense that if I was debugging something, okay, and I was writing a program, I would just go to notebooks, which is where I'm just playing around right now. I can at any time just take a look at this file. Okay, I can open it up in any text editor I like. Okay, and there's the file. Every row is a bunch of numbers, and I can see them all spaced out. Okay, and you can see that you can really read what's going on. We can use all the standard tools like head and txt to only look at a few of the rows. And it can be a very compact way of debugging it to use these textual representations. And I have seen many a software project where someone writes some code, they get it working with a text-based file format. It works fine, so they don't think about it too much. And then they come along and they say, well, my computer is faster, so why don't I just go and make my problem bigger? And then they go and they save it as a text file, and your very small 245K file starts to now become a 24 megabyte file. Okay, and you go, well, that's not too bad. But remember disks, right? Floppy disks are only about a meg a piece. This file format takes a lot more space than this file format. And if it's longer to save it, it's longer to read it, it's more network bandwidth. So we care about how we store these things so we're able to use them efficiently. Now, you can do better, right? We talked about compression, right? So I can take either one of those file formats. I can take the NumPy one, or I can take that text file one. Okay, and again, I'm going to compress these things. When I compress them, okay, compression on text files, because it's the exact same string again and again and again, compression can work incredibly well, but compression works fine on binary file formats as well. So what you want in a storage method is not just binary versus text. You also want to look at the compression algorithm you're using, because you can start to save a ridiculous amount of space on your disk. Hard drives have less capacity than RAM does. Hard drives are much slower. This is the order of operations again, right? You know, writing to disk is much faster than writing from RAM. Just as an aside for those of you who need the refresher, you know how computers have CPUs and they have registers, right? When you're getting something from a register, it's like picking something up off your desk and putting it down. Getting something from RAM is like walking downstairs of a 10-floor building and picking up something from the driveway. And getting something from the hard disk is like getting in a 18th century sailing vessel and sailing off to Australia to get your object and then coming back to get you, right? Those are sort of the orders of magnitude about how slow disk access is compared to RAM and like cache It's gigantically different. And we're not even talking about network latency. Yikes, that's crazy. So the point is, thinking about your storage format, if I can get this data as 62 kilobytes as opposed to 25 megabytes, that's going to really, really matter one way or the other. So when you're creating data, think about how this data is being stored. Think about how to access it. Now, CSVs have value. And the reason they have value, the reason that people put their CSV data in, is because if it's only a few hundred lines, who really cares? And the tools needed to load it up are that much easier. If I was to hand someone this file, a.np.mpy.gz file, and I just was to ship it off to somebody, sure, it's really highly compressed. But my guess is, before learning about Python, you wouldn't have any clue what that file is. If you just opened up that file on your desktop, you double-clicked on it, Windows would say, what application would you like to use to open that? I don't recognize it. It's not one that I'm used to. CSVs, double-click on it, Excel will almost for sure pop up if you're on a sort of standard Windows machine or OpenOffice, right? In terms of what's inside an NP file, so an NPZ is a gzipped NP file. An NP file is just an array. It's just a binary, like it's not a pickle. It's not pickled in terms of that. Pickle is another data type for Python objects where it serializes the data type. You can pickle lumpy arrays. These are just flat arrays, like it says, this is the data type, and here are the numbers in that data type. And that's it. In fact, you can see it right here. You see how it's 8,128? Well, the file format, the 128 bytes right here, is describing this is an array which is 1,000 by 1,000 of type float 64, 8 byte floats. And then there are 8 bytes for every float and 1,000,000 numbers. So it's just a straight dumping into the disk as a binary file format. It would not be hard to write a piece of code in C or Fortran to read this in if you needed to, but you still have to write it in. So the trade-off here in terms of these file formats is ease of use versus storage and speed, and there's always a trade-off between those two things. Okay, let's talk about some other file formats, namely not so much NumPy, but historically Fortran is a language that has been used in lots of different scientific applications, right? So, for example, PyMagic CC or PyMagic C is one of the project topics I've said you could do. What is it? What it is a Python wrapper around a climate model called Magic C. Okay, so let's take a look at Magic C. Okay, it's a climate simulator. It's supposed to simulate how warm our planet's going to be into the future. Okay, and if you actually go and you take a look at it as a piece of code, okay, what you see is this Magic CC. Okay, it's a Python package, but inside of it, it's got this code for doing input output. That's what IO represents. So to make this package work, it needs to be able to read in the output from Magic C. Magic C is a program. Okay, so I'm just going to, being not super familiar with this all the way through. This is what, that's sort of not what I was looking for. In files? No, not input files. Okay, so if you were given a binary file format, okay, so something from a language like Fortran, if you have to read and write that data, you have to start thinking about it at that low level, okay? Values in Fortran binary streams begin and end with the number of bytes, okay? So it reads something into memory, and then it actually has to think about it as being an array, and you have to care about how many bytes, you have to care about how big each byte is, and you very carefully have to go through some work to be able to turn this into an array, okay? So you see how it's required that many lines of code to get me back an array. And the reason is I don't have dealing with a file format like a NumPy file format. I'm dealing with a very low level format from Fortran called unformatted binary. It's just a string of bytes to the disk, and an unformatted binary, it's unformatted. There's no metadata. There's no little header that says what the data type is or how many numbers there are, right? All you get is a sequence of numbers, and it's up to you as the reader of that data to interpret it correctly. This requirement to interpret the data correctly makes it very fast. The computer doesn't care, but it slows us as humans down a lot. It means that if you hand someone the output from this computer model as a Fortran unformatted file, two things. One is they have to write code to be able to read it. And two, you haven't really described what's even in the file. All it's going to be is the straight numbers. And so I'll show you a little bit of Fortran. Some of you may have never seen Fortran before. So Magic 6, this is, I thought there was some Fortran in here. Data files, you already see they're using some CSVs in there as well. I thought there was some Fortran in here. It doesn't matter. You don't need to see Fortran. The point being, what you're going to get inside of these codes is a line. It looks a lot like a print statement. It's called a write statement in Fortran, and it just writes an array to disk, but it does it with no file format. It's just a straight binary stream. And when you're dealing with those unformatted binary formats, what you have to do is you have to be careful, because reading them back in is going to require a lot of work. Here we go. Here is another. This is on a climate model. This is an idealized ocean model, and it has some Fortran code in it. So we'll jump to there as an example. So this is what Fortran code looks like. Doesn't matter what it looks like, but it's like many other languages. It does have modules. It has the ability to import modules from other files. This is how you define a subroutine, which is similar to a function, but not quite. In Fortran, here is the dumping, which is a fancy way of saying saving, and you have all of these variables. You'll notice that in Fortran, you have to be specific about types. So H is a double precision array with these dimensions. It's a three-dimensional array. HAV has these dimensions. U has these dimensions. So these are many, many arrays which are being passed in. When we go down to the code, which is how do I write this? Every one of these things is calling a function, write output 3D. This is how you call a function in Fortran. Okay, so what does it do? What it's doing is it's passing the H variable or the U variable, the V variable. And because Fortran's fairly low level, you don't just pass in the array, you actually need to pass in all of the metadata, the sizes of the array into this file. And if we actually take a look at what write output 3D does, I'm sure it's going to be in here. I know it's going to be in here because that's where I would put it if I was writing this program. There we go. Write output 3D. Again, it's just taking in a generic array. This is what writing looks like in Fortran. It's super low level. All you're doing is you're opening up a file handle. Okay, you're opening up the file. Unit 10 just means file handle 10. And then you're going to write the final handle 10. You're just going to write the array. And it's literally just a dump of the exact same values in memory right to the file with absolutely no metadata. There's no information about how big the array is, what the array is, what the data types in the array is. It just writes super fast, but really useless outside of the model because the order in which you write it is not there. You don't know what the dimensions are. You don't even know the order of the things. Is it row column or column row? None of that is buried in it. So to read these files requires a lot of work down the road. You will notice in a lot of Fortran code, very early versions of Fortran code will just do things like this. And that's because when your Fortran developer is doing it, This is easy. I can just dump it to the disk really quickly. To make it cleaner, I have to do a lot more work in Fortran so that things are easier on the other side. And just for comparison, all this stuff about passing the sizes in the array, I want to compare to what NumPy is able to give us. We have an array. I said save. Okay. I didn't have to create a function that passed the 1,000, the 1,000, the float. I just said save. And inside this file has all of the metadata to recreate it as it is. These challenges we've had historically in science with these unformatted binary formats, okay, or formats that have very specialized formats, have led to the development of standardized scientific file formats for array data. I'll give you one more example before I go into this. Here is a piece of code, Capitan, which does linear potential flow. Okay, that's fluid dynamics. It's just looking at the flow inside of some geometry, and this module or whatever it does, it has some sort of grid, and it's looking how fast a fluid like air or water or fuel goes through something. I'm looking for a picture. You know, pictures are fun. Yeah, there we go. Here's a little picture. There's a little boat, and you see the boats bobbing up and down. Make the boat bigger. You can see the boats bobbing up and down, but more so, these waves are coming along, and the boat itself becomes a source of waves. So that problem of what is the wave field around a boat, that's something that this program can solve. Okay. Well, if you're solving this program, what you need to do is you need to have what's called a mesh. If you've ever taken a course, and since we're in scientific computing, you probably have done a course in matrix methods and other ways of solving numerical problems. We typically have a mesh or a grid. The creation of that mesh or grid, you need a file format. You need some way of storing it. Every proprietary company out there who makes a computational fluid dynamics package has their own grid format, and it's a mess, okay? So this is just a snapshot of some of the mesh formats that I was seeing being accepted by the authors of the Capitan program. Radios, Hydrostore, TechPlot, NAT, WAMET, Nemo, Mish, Vermal. Some of these are standards. Many of these are proprietary, closed software tools that to create them, you're supposed to buy a copy of the actual software that created them or read them, right? It's only when these standards have been opened or standardized that I can write new software to be able to read them in. This barrier to being able to actually access the data is a real problem. Just as an aside, you know that we're currently going through a resurgence in transparency in government, right? So you might have been familiar, and lots of countries that do this. I'll just, because Canadian University, I'll talk about open data. There is a movement within Canada and several other countries and provinces and cities to make the actual data that we work with public and accessible, okay? And in all sorts of areas, not just in science and technology, but in transportation and education. And so the idea is to push that data up into the web so that anybody could take that data, really see how government works, and maybe build something on top of it. There are data sets in here that are only readable with proprietary software. I don't know if I'm going to find one by looking at it really quickly, but I remember seeing a data set in a British open data set, which was the transportation network of the country, but it was saved in a geospatial information system file format. So there was no way to load the data in without buying a license to the software that lets you read it in. And so that's a barrier to be able to access your data. It's also a barrier because software stops working. If you've ever tried to run an old piece of software on a new computer, you will find that things just don't work anymore. And the reason they don't work anymore is the software developers who wrote that piece of software 5 years ago, 10 years ago, 30 years ago, maybe stopped maintaining it for the newer computer. You may not have hardware available to run the software to access your data. Okay, so given that challenge of when we have file formats that are either proprietary or undocumented, there has been a move to develop standardized file formats that can be used across different disciplines that at least explain what we're going to put in the file and how we're going to do it. And so one of the ways that this software package uses to save its output, it doesn't invent the Capitan file format. It doesn't even use the NumPy file format because NumPy is actually quite niche. It's quite specialized. It uses something called the netcdf format. And net is a word for network, as in, like, you got to remember the history of some of this stuff is as the internet started to become a thing and people started sharing their files over the network, the net, you introduce the net version. The network common data format is an extension or an evolution of what was originally called the common data format. And it was a way of storing arrays onto disk so you could actually look at them. And so there are bindings so that if you're writing your program in C or C++ or Java or Fortran, any one of those languages, it's easy to save data to netcdf. And it doesn't matter if you're using Python or IDL or MATLAB or R or Perl, you can read or write to these formats as well. Some of the features of netcdf and any good scientific data structure are going to be that it's self-describing. What that means is you don't need a separate file or a separate piece of documentation that explains what's inside of the file. Okay, and again, an unformatted binary Fortran thing is just a string of numbers. You need some other file to tell you the dimensions of the array, the data type. A netcdf file has within it enough metadata to explain what it's about. It's portable. Okay. Now, we haven't talked about this much, but in the history of computers, we've been doing scientific computing for a long, long time. There is a choice of how you actually are going to go representing a number inside of a CPU. Okay. And I don't know if you've ever heard of this phrase, but has anyone ever come across this word, endianness? Okay, this isn't Gulliver's Travels. This is little endian and big endian. Okay, it has to do with how numbers are stored in computer memory. Now, normally when we write down a number, right? In base 10, we tend to write down the largest, most significant figure first, right? If I'm going to write down the number 1,234. Okay, let me just do this here. Okay, so let's do this here. Okay, this is an example of a big endian type thing. If I want to write down the number 1, 2, 3, 4, what I'm going to do is, as I write it, I'm going to write a 1, and then I'm going to write a 2, and then I'm going to write a 3, and then I'm going to write a 4. And the idea is, okay, I'm dealing with the thousands, the hundreds, the tens, and the units, okay? Like you've done, this is like grade school math or grade 1, grade 2 math or whatever it is, placeholders. That's a big endian sort of way of thinking about it. And there are computers that read and write numbers like that. But there's a bit of a problem with thinking about numbers like this, which is if I read in the 1, I don't actually know how big the number is, right? So if I'm just reading the 1, and I just say 1, you go, well, is that 1, 100, 1, 1,000, 1, 1, whatever? And it's only at the end you can figure out what it is. Instead, if we were, no, that's actually not proper Python, so that's why that won't work. Instead, and I'm putting this, I'll put this in quotes because this isn't exactly what little endian is. It's all done in binary, not in base 10, but it's the right idea. If I wanted to store the number 1, 2, 3, 4, what I could do in a little endian sort of framework, because I could say 4, 3, 2, 1. I could write, I could communicate. I'm always going to give you the lowest significant digit first. I could say my number is 4321. And what you could say is, oh, well, the first thing you give me is the units. The second thing you give me is the tens. The third is the hundreds. The fourth is the thousands. Oh, I'm done. So I can build up the number in order all the way through. Large scale, big iron, cray supercomputer kind of stuff historically has been big Indian. Intel, as in the Intel 8086 x86 architecture, is a little Indian format. So computers we interact with are often little Indian. Computers that are supercomputers, up until the fact that Intel took over the supercomputer market, were big Indian. And that meant that if I give you two files and I said, here's a string of bytes, and every 8 bytes represents one floating point number, I still would also need to say, right. This file is written down in this format, 1, 2, 3, 4, but that format's written in 4, 3, 2, 1. This is a portability issue. It means a file that you read and wrote on one system may not work on another system. And that's why we say for wherever it is, I've got too many windows open now. No. I will find it. Or if I can't, there it is. That's what we mean by portable. It agrees on how things are going to be stored. And there's a few other things that you want it to be scalable. You want it to be able to work through remote servers on over network access. You want to be able to add to it. You want to be able to do things that support multiprocessing. And you also want to make sure that's archivable. And this is a key idea. Archivable is the statement that this file format is going to be documented in such a way, so even if you just throw this data on an optical storage medium on some CD-ROM and leave it in a filing cabinet for 45 years, you will be able to, in a future version of the software, still read the old file. These are features of any file format you want if it's going to be the basis of your scientific data. It doesn't have to be NetCDF, but it needs to have at least this set of criteria to it. And these are some of the things that we put on there. I see in the Slack that we've talked about Avro and Parquet as being other self-describing formats. Yep. So those are typically coming from the world where data, it's sort of like a CSV file superhero version, right? It's a binary stream. The idea is you're thinking about records coming in sequence, not necessarily line by line, but for data frames, right? It's a way of storing data in a table and streaming that data, right? A way of sending data and accessing it from the disk. So the Avro with Arrow and Parquet are other data formats. The difference between Parquet and Avro and something and CSV and something NetCDF has to do with its ability to store higher dimensional data. Okay, CSV files, Parquet, I believe Avro. I'm not so sure. I haven't used Avro myself personally. They're great for two-dimensional tables, right? Columns and rows, no problem. But a lot of data in the sciences is multidimensional, 3-dimensional, 4-dimensional, 5-dimensional, 12-dimensional, and you need file formats that make sense for doing that kind of thing. Okay, let me just see if I can talk about these file formats anymore. Okay, so here's one from Small Body Planetary Astronomy. It uses FITS, CSV, text files, and JSON. Okay, we talked about JSON a little bit. So this is a text file. This is a text format. So it's typically in using like characters, like Unicode encoded characters. The trick is with JSON is it can have more complicated data structures. CSV files are always just columns and rows. That's all it understands. JSONs can incorporate the idea of arrays of arrays, dictionaries or maps, and other ways of putting stuff together with multiple data types, right? So there's ways of storing that data together. You will find that the web in terms of how we pass data to and from websites to clients and back and forth. JSON, these sort of blocks of text that represent something, is becoming a more and more common way of exchanging that data from a network to where you happen to be. This actually gets to an interesting point. A lot of the work on file formats were developed in a time and a place where if you had data, you wanted to save it to a hard disk or a tape, right, or something like that. And if I was going to move it to another facility or another thing, what I would do is I would take that data, copy it onto a magnetic tape or a hard drive, physically pick that hard drive up and walk it to another machine and plug it in. And what that means is the assumption for a lot of code is when you're writing or reading from the disk, there's a disk. There's something you actually can read from. All the technology about caching that we put into hard drives is based on the fact that when you're doing reading, you're able to read ahead of a certain number of blocks on the disk. You're able to think about how that data comes to you. Well, if you've noticed, you're probably listening to me right now on a computer. If you're on a laptop, look to the side of that laptop. Where's your CD-ROM drive? You probably don't have one. You definitely don't have a floppy disk drive. You may have a USB flash key that you could use for data storage, but you might not, right? There are lots of devices that are computers. I'll show up my phone as an example. There is no external storage on this thing, right? There's nothing you can save it to all the way through. How do we save data in this modern world? We send things over the network. And what that means is file formats or data serialization over a network is a different problem than saving data to disk. And some of the file formats which work fantastically over disk don't actually work so well over the network. JSON is a file format which makes sense to save it as you're communicating from one computer to another and to stream it. But I don't know if I would save on disk large blocks of JSON. It's a lot of text in there, a lot of white space. There's more compressed ways of doing it. Likewise, a file format like netcdf, as much as it says scalable, okay, it turns out that netcdf, though is scalable, isn't scalable enough. When we start to do really truly distributed computing, right, tens or hundreds or thousands of CPUs, the way that netcdf as a file format is designed, it's assuming that on one computer or on one collection of hard disks, the entire file is there. There are data storage models now, not block storage, but object storage, where files and data is not stored on a single file system. The data is spread across many, many file systems. And you can think of Amazon Web Services or how Google stores things. There is no one hard disk which contains the Google database, right? There is not one data center that contains the Google database. It's all in one file. It's distributed across many, many different spots. So there has to be some evolution in these data formats to be able to accept these new types of data, to be able to work with that. So there has been movement in this field to develop other sorts of data sets which are appropriate to that. So just as a snapshot out there, here is one that did not exist 4 years ago that I'm seeing as more and more. ZAR, the Z array, ZAR, is a format, I'll make it big enough so you can see it, for chunked, compressed, n-dimensional arrays. Okay, so this is a file format which understands that when you're reading and writing, you may want to not read a single number at a time. You want to write a block of data at a time. Compression, as we've learned, is essential. Maybe you don't want to compress the entire file. Maybe you only want to compress blocks or chunks of the file separately. And the reason you do that is so when you go to uncompress it, you don't have to uncompress the whole file. Parquet and Avro have similar functionality. The thing with ZAR is it's for n-dimensional arrays. ZAR is a young project that's being worked on but it's possible that it will form part of the storage model for the next version of NetCDF. NetCDF is sort of a data model about how things are laid out, but NetCDF is actually not telling you how the data is stored on the disk. The current version of NetCDF uses a storage model called HDF5. HDF5 is the hierarchical data format. It's assuming that files storing scientific data, it could be big, they can have really fast input and output, the data can be different. But one of the things is this file format is not amenable to is distributed data sets that are spread over multiple computers concurrently. Okay, so this is a great file format for fast input output. So you have a high performance computing or some RAID system, but it's not an appropriate file format. So there's always work going on in terms of developing new file formats that are appropriate to the technology we have. At the same time, because everybody who writes the scientific software doesn't want to have to go into the details of what's an HDF5 file, what's a ZAR file, what's a NetCDF file. All of these packages, what we do is we develop libraries or toolkits or ways of loading that data in, so we're able to access it. Anyways, okay, I'm going to take a 10-minute break at this point. And we'll come back to it. I want to talk a little bit about data storage in terms of something called FTP and different web services to finish off this lecture, and then I'm going to get into a slightly different topic. But I think I've been yammering for a while. Might be a good time for a break, so I will put into Slack. I don't know, and again, I just need to do the math here. It is 2:30. Back at 2:30. I'll say that's right here. Back at, I think I got the clock right. Oh, sorry. There, I'll say this. I think we should take a small break so people can stand up, stretch, and we'll continue this in a moment. Well, hello, everyone. I guess we'll get back to it. Thanks very much for the break. I appreciate it. What I want to conclude with in terms of this sort of discussion on data storage formats is the need to be able to get to the data and distribute your data. One of the things that's changing in several different research councils around the world is the recognition that science isn't really done until not only have you communicated your science like in a publication, but shared your science or the data behind your science so that other people can go and pursue it. And so being written into various funding bodies, rules, and regulations is we as researchers have to provide a mechanism or a plan on what we're going to do about our data. How are we going to make it available to others if and when they want it? And this is a challenge. It's a challenge because we're not quite sure how to pay for it. We're not quite sure what kind of data we want to make available. What is really needed? Do I need to make everything available? And for large data sets, what does that even mean? Do you truly want every temporary file that I made when I'm compiling my software? What do you mean by the data? So these are questions that are being actively considered. In terms of historic ways of making the data out there, you might be familiar with the acronym FTP, or File Transfer Protocol. Now, a file transfer protocol, very historic way of sending files from one network location to another network location. FTP predates the web, right? So we talked about the internet. You know, the internet's not the same as the web. The web only got invented like 20 years into the lifespan of the internet. FTP predates that. And so it's an older protocol for sending files back and forth. Because it's old, it had been historically pretty standardized. So just like you can go to an HTTP website, you can go to an FTP website, well, not a website, an FTP, and you can go to something. Now, FTP is not secure. It's not secure in the sense that if someone is watching the network, they can see the data that's being sent over. And for scientific data, that might be just fine. But we recognize that in our security conscious world now, we don't like to have unencrypted data flying over across the wire. So web browsers used to have built into them FTP browsers. And nowadays, what you have to do is you have to use a different client just to get access to FTP. FTP is a command line program, but you're going to find out that more and more servers are disabling their FTP protocols. And in fact, I'm now seeing more and more clients are making it difficult to access FTP data. It's not as easy to access the data. Now, if you're not familiar with FTP, don't worry about it. It's going out. If you are, you know that it's a command line based thing where there's puts and gets of files. There have been developments where people have taken the same data, which is available through FTP, and made it available through an HTTP interface. So now I'm able to click and point and you see directories, but all this really is a layer that's sitting on top of an FTP server, or the same data as an FTP server, but it's being sent over to the client over a secured, encrypted HTTPS protocol. Anyways, what do you typically see when you open up the data in this way? It looks a lot like files that you might see on anyone's hard drive, right? You're going to have a directory, and inside the directory, there's going to be a subdirectory, and inside the subdirectory, there's going to be another subdirectory, and inside that subdirectory, I'm just waiting for the subdirectory to load in terms of how long it's going to take. CSIRO is the Commonwealth Science and Industry Research Organization. It's the Australian NSERC. No, take that back. It's the Australian NRC, National Research Council of Canada. Okay, well, that didn't even work. Well, this is sad. I want to see some data. Oh, okay. Well, here we go. Here is a link. They're just files. So the way that whether it's HTTP or FTP work is you go to a particular path and you download a file. And you can see that these files, this is from April and May, this is recent data. This data is just indicating by a number, a tag, and an extension. The extension stands for netcdf. And the reason this works is because netcdf is self-describing. So you could download this file and then open it up to see information about where this was. This particular data set is from Argo. Same thing that the assignment 7 was based on. You know that the Argo data sets are these profiles. Each one of these things is a different profile. And what you're doing is you're seeing it going up or down at a particular location. Once it goes into here, it gets sorted by location. So here's all the data for, say, 2020, right? So if I wanted to get a record from a particular ocean in a particular year, in a particular month, these are all the records from that data, okay? So what this is doing is giving us a way of getting the data for any one particular float where it happened to be at a particular time, and you could download this file. I could click on this and I could download it. And because it's a netcdf file, I'd be able to open it up with any number of tools and look at it. But the challenge with FTP or HTTP as ways of getting with data is if I want to ask a question not about any one of these files, but all of these files, life would be a challenge. And the reason it would be a challenge is we have, for every ocean, you have 12 months and you have 12 years. There are 3,000 floats that have been collecting data for up to 10 years in this data set. There are files upon files upon files. There are thousands and thousands and hundreds of thousands of files out there. And so the issue becomes, well, how do I get the data so I can ask a question about it? So for this data, they're measuring the ocean. One of the things they're measuring is the temperature. So you may want to ask a fairly simple question. What's the average temperature of the ocean, grouped by day or grouped by year? And is the temperature of the ocean increasing over time or not? Sounds like a pretty simple question. However, to answer the question, when the data is made available in this file-based way, requires first downloading each and every one of those files. And just like walking through a file system takes a bit of work, walking through a file system of HTTP or FTP takes some work. Now, often what they'll do is give you metadata files that give you that index, but there's a lot of effort to be able to do that. Over time, various services have been developed to give you access to the data instead of giving you access to the low-level file. And I don't mean access to the data like a visualization of it. Like, there are services which will give you a plot of the data, okay? So there are tools like this. So this is something for Argo that's showing me every Argo float, and I click on a dot, and it gives me this particular data right there. And there's all of the charts and graphs that I may want, okay? But if you're a scientist, looking at the charts and graphs is sort of cool, but you probably want the actual numbers. You're like, yeah, this is great, but I need in like a CSV file what the data is, or an SCDF file, you know, something I can do something with. And if you look on this page, you see the data as curves, and we're like, well, I want to download the data. Now there is one link here that says download the data as JSON. So this is an example of a site which is providing a computer way of accessing the data. So what you can do is you can click on it and you can get the data as JSON. Now, JSON, as I said before, here's an example of what JSON looks like. Okay, it's a bunch of dictionaries. So key, value, key, value, key, value. Because it's a bunch of key values, we can make it prettier, right? Just formatting it a bit. And you can really see that the data is pressure, salinity, and temperature. PSAL stands for practical salinity. And then there's a bunch of measurements. And here's the measurements. Measurement number 1, temperature, salinity, pressure. Temperature, salinity, pressure. Temperature, salinity, pressure. Temperature, salinity, pressure. Now, this is JSON. And this is how we represent data in JSON. Okay, every data point, a particular temperature, salinity, and pressure is represented by these characters. Remember when we talked about ease of use versus storage and efficiency? To store a temperature, a salinity, and pressure is requiring this character, this character, these characters, this character, this character, and this character, these characters, these characters, and these characters. And they're repeated again and again and again and again. And in fact, these things aren't even being stored as binaries. They're being stored as textual representation. There's a more compact way of sharing this data. So even though this service is offering the data as JSON, if you actually wanted to pull down not one profile, but you wanted to pull down hundreds of thousands of profiles, this wouldn't be a great way of doing it. It could be for some applications, but not for others. So is there a middle ground between downloading all of the files and doing your own local processing and using these tools that are giving you the data, but they're not efficient enough because I want lots of it? And there are tools that are being developed that are in the middle ground. And this is for oceanography, but the story works for every discipline. ERDAP is a technology in the environmental sciences, atmospheric, climate type world that gives you a interface to the data. So these data, it's actually stored internally as a netcdf file. These are all the columns, these are all the variables. So what you can do with this interface is you can select certain fields and say, well, I want all the files where the date is within a certain range. I want all of the files where the pressures are a certain range. And I want all the files in a certain range of location. Somewhere in here, it's going to be which ocean it's in. Oh, latitude and longitude. So the way a software like this works is they've indexed all of the files and are using something equivalent to a SQL database in the back end. It probably is Postgres. That allows you to do queries on this. And then what this tool is doing is it generates the data back for you. So if we just look for some data, okay, so let's look for some data. Let's look for data let's uncheck everything. All we're going to care about is latitude, longitude. How about pressure and temperature? And we're going to care about time, right? We care about when. Okay. So to make this more concrete, let's talk about data only collected. Well, what's the date today? Today is the 6th, since the beginning of June. So what I'm doing, I'm saying, give me all the records from the beginning of June. And this is a little interface to be able to do this. Okay. And this is sort of a cool little application, and whether or not it's for ERDAP or something like else, what it's doing is it's finding all of the files over the whole system which have data from the last 10 days. Let's say I have an error. Even that might be too much. How about the last day? Like since midnight last night, you're going to be able to do that for me? It's thinking. It's thinking. That really should be more doable. Obviously, I have now just broken this French site. Please be patient. It may take a while to get the data. Because what it's doing behind the scenes is it's opening a bunch of files and looking, and I wanted the data from today. Just give me data from today. Anyways, I don't really care about what the data looks like. What I care about is what it's doing for me. What it's doing for me is it's creating a, oh, there's the data. Okay, so the data is being rendered as a table. Okay, so this might be a way of accessing the data. It's times, latitudes, longitudes, and pressures for all of the Argo floats which generated data, well, today in the last 24 hours. Okay, so this data set we could query it a little bit more tightly so that we could reduce it down. But what's been sent back to us is a web page, in the sense that if I was to actually, okay, I'm going to stop loading this because this is a lot of data. Maybe I can't stop loading it. If you know anything about how web pages in HTML work, this is a table. Okay. Has anyone done any like hand coding of HTML tables? You know, all the TDs and TRs? Well, every one of these things has a TR, TD, 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 TR, right? This is a very long file to download because it's very verbose. And I've broken Firefox. It does not like that anymore. Well, that's just too bad. Go back. I want to go back. I want to stop. Okay, we're killing that because that's just too much data for life. These interfaces, though, don't have to bring back data which is HTML. What this tool is able to do is actually bring this data in a whole bunch of different formats, including CSV. So if you wanted this data to be available as a CSV file, it will download that data as a CSV file. Or if you wanted it as a JSON, you could get it as a JSON. Or if you wanted that data as a netCDF file, NC, it could do that. So there are usually tools that sit between your data and you that will do some pre-processing and selection of it. And so you'll see for every domain of science, some set of tools being developed for there that give access to the data. And there's a lot of work in this area. What should this tool actually look like? How should it work? Can it be programmed, right? When we do these calls, they're actually just REST APIs, right? So there's web services. You pass a bunch of things as a GET request, you get back the data. The data could be a web page. It also could be a netCDF file or a CSV file or whatever you want. So these data storage, these platforms, people think about and put work into, how am I going to make this data accessible? Okay, just for one final example, let's move away from oceanography into something completely different. Let's talk about this package, phase space, an n-body phase space generation in Python. Okay, what does that mean? Simulated particle decays are common in experimental particle physics. Okay, so what we're talking about here is high energy particle physics. Back to that CERN, a Large Hadron Collider, it does simulations in that world. And if you actually go and you look at the data, software repository, you're like, okay, well, how does this work? I go into the data directory to see some sample data. They've got these things. They're .root files. Okay, it's a raw file. Okay, like I can download it, but I need to have a root viewer. So at this point, you go, well, what's a root? How do I read a root? There is hooks to be able to open that data inside the phase space routine, but it's not something we're able to look at right away. So if you dig into a little bit of what is phase space and what is root, you very quickly figure out that at CERN, they have been dealing with large data for a long time. And so root is a platform or an ecosystem for analyzing vast amounts of data from high energy particle simulators. Okay, and just to give you a sense on where this fits in the scheme of things. Okay, what is root? What is this thing? Well, what root is a software framework for doing data analysis and input-output. Okay, it's written so that people who are comfortable with C++ as a language can, rather than writing a program, type in pieces of C++ like syntax and get answers in an interactive sort of way. So you can do things like download, get the data, select the data, plot the data. And there are a bunch of tools that make plots that are appropriate for high energy physics. Okay, so this is what root looks like as an interpreter. You type in root, and then after root, you can type in numbers and you can do math. Okay, you type in root things that look like C++, but sort of in an interactive kind of way. So if you want to have a string, an array of doubles, go ahead. You can have a function which does an argument on each one of those arrays. And again, if you understand C++, you'll see what this is doing. If not, it's a function, okay, that is basically going to convert every one of these numbers into another number, okay? And then there's functions like sorting, and it's all built in here. And it works for this community because C++ was their go-to language. And so this makes it a very quick way of interacting with data. But I hope what you can see is the way of using it. Doing mathematics, bringing in data, like creating an array of doubles. This is something you can do with Python and NumPy. Why does this root thing even exist? Functions, TF1, F sign. Well, that's just going to make a plot. That's just going to make a plot just like I could do in Matplotlib. And so I got a question for you. If we've talked about Python, we've talked about NumPy, and we've talked about Matplotlib, why would an organization like CERN go through the trouble of developing this system like it? Why would a community make a piece of code? I don't know about you, but C++ is not like, read that line for me. Okay, C++ is not a easy language, highly readable language. That does not count as readable, right? Legacy, and Yashar is right. Root has been going on for far longer than NumPy and Matplotlib have existed. Root sort of would be, the people who invented this said these are what these ecosystems need to have in it. And I would say that NumPy and Matplotlib have borrowed a lot of things about what these tools need to be. Now, in terms of people being trained, right? You're going to school, you're learning about Python, you're not going to learn about root. If one of you gets a job working at the CERN high energy physics platform, you may go, yeah, I'm not familiar with this. I know all this cool Python stuff. And in fact, what I'm finding is tools like root are getting Python bindings. So if you actually took a look at the manual for this environment, one of the things you're gonna see is information about C++ or Python. So what they're doing is they're creating Python bindings to this environment. Effectively, it's because more and more of this stuff is already being done in the Python ecosystem. And so they're keeping only the parts they really need to in the root system. This is normal, okay? I wanted to find, I don't know if I'll be able to find it, images. I thought there was somewhere. Graphics. Oh, well, that's why I made a copy of it. Here we go. Here is, and this is an older plot, but it's actually quite neat from a bit of computer history. I lost it. That's the plot that I want that link right there. Go. Okay, here we go. Here is, and I said this plot is from 2010, so excuse the resolution, but that's just what was looking pretty good in 10, 12 years ago. You can see that in the history of high energy particle physics since 1970, okay, so this is going back a little while. Depending on the era, different CPU architectures have been used, right? A CDC back in the 70s, then there was the era of the Crays and the Vaxes. We now are in the era of Linux, and we're almost actually monoculture in the sense that Linux dominates this sphere entirely. In terms of languages, Fortran in the 70s, Fortran 77, though it still exists and is strong, this up to 2010, C++ was dominant. But my guess is if you were to continue this diagram to 2020, you'd actually see C++ die off a little bit as well. Code management, okay? The code management system I've been talking about has been Git. Git isn't even on this diagram. It did not exist, right? Before Git, there was SVN. Before SVN, there was CVS. Before CVS, there was something. These technologies always go through evolutions. There has always been a code management thing. So you're learning about Git, not because Git and its syntax is important. You're learning the fact that there has to be a component that is Git-like. If there isn't, you need it. Before root, there was this thing called Zebra that lived for about 20 years. And my guess is root for both graphics, histograms, all that kind of stuff will die out. And my bet is Python, because people are familiar with it, will grow and become the dominant scripting interpreter for this current 10-year cycle. 10 years from now, I have no idea what the history will get into. But there is this ebb and flow in terms of which technologies we use. The specifics are not important, but know that at any time, there is going to be some sort of scripting language out there. This course itself used to be a third on Python, a third on Perl, and a third on TK as 3 scripting languages, which were sort of popular. Very few people use TK anymore. Very few people use Perl. Python and R, I would say now, are dominant open source scientific languages. Julia might come in to displace them in the future. I can't tell you. But you should always be looking for what these tools are. There will always be a tool like this out there. Okay, and there's more, and we could go into any one of these packages to take a look at what's on there. Seismology, right? Seismology, form factors. What I found was you have to go to a subfactor called obfspi. Here are all the file formats in seismology that are out there. Okay, every one of these directories is a file format that you use in seismology. So acoustics is something you do in seismology. So here is the code to open up and read an audio wave file. It's a way of storing a sequence of data. And you can see that you have to be very specific about the data types that are in there. And you're loading things up file by file, right? How do you read it? You're reading this thing in as a type of stream of data and decompressing it at a certain resolution. So these ideas are shared across all these different file formats. Lower level file formats require more code. Higher level file formats that have library support, Usually there's an API that you can use to work with it. You choose the right file format for your community. There might be one that's already established. You don't try and go to the astronomy community and say, hey, we're going to use NetCDF. It's so cool. You go, oh, you guys have been using FITS for 40 years? You probably want to keep on using that, right? Yep. Okay. In oceanography, it doesn't matter if we invent something new. NetCDF is going to stick around for quite a while because there's a lot of heritage to it. That doesn't mean we can't change ways we work with it or how it's built underneath. But there's those community-based ones. But there is a move, and formats like Avro and Parquet and Czar are all speaking to the fact that all of us are writing these tools. Wouldn't it be great that rather than having to write a piece of software that computes from format A to format B, we could write our software so that any format gets converted into an intermediate format, which is shared, and then that shared format can go out to format B. And I'm seeing that as a transition in the maintenance of the open source data science, computational science world that's out there. Anyways, so that's just a survey and a review of kind of thing that out there. We've got two things we could go and do now. I got about another hour of my time, your time, in terms of doing it. One is if you'd like to have a discussion on the project, or specifically any particular component of the project that you're actively working on, we definitely could do that. I am going to remind you that projects, CMC, oh, wait. No, I don't want marine heat waves. That's something else I was working on. There we go. So what I've asked you all to do is go to this project, and just like we did with the practical Python thing, I wanted you to fork it. And then on your own copy, make a change to a single file. And you can do this all inside GitHub. Okay. So what I mean by a change is I want you to go to projects.md. I want you to edit this file. Now you can download and edit it, or you can just do it right in the viewer and add in a line. And what I want you to add in is whatever your name is, what your project you're doing, what the topic is, and then a link to your project page. Okay. Once you make that change, because it's on your fork, what'll happen is GitHub will say, hey, you've done something. Do you want to submit a pull request? And what happens on my end is I get this little message that says, Vivek said I added a project title. And so I can come along and say, looks good. And if I care to, I could take a look at what the code is, and I can see that what you did is you added some code. Your code is, you added, oh, PyMagic CC. You want to do that one as well. That's wonderful. I love it. And I'll go, that looks great. That's a great fix. I love that project. I'll merge the pull request. And now everybody is able to see that projects.md now has 1, 2, 3, 4, 5, 6, 7, 8, 9 different objects, right? So we are at 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 project topics, but I think there are 19 people taking this course. We're supposed to be presenting these things in 1 week. So we're getting close to that crunch time of you really should have something you're working on by now. And if you are working on something, you just haven't communicated it with me, that's okay too. I'm just really hoping that more than just 8 people have started this. It's supposed to be worth about 2 weeks of work, and we've had 1 week. So please don't leave it to the end of next week. In terms of what we're needing to have done, it's due in a week. It's due next Thursday, because I want to have you present your work to each other. I want to have you do a bit of a peer review with each other so you can sort of see what each other's doing. Try and have at least part of the project done for next Thursday. If you need a few more days, the weekend to the middle of the next week, there's no exam in this course. It would take me a while to mark them anyways. I am fine if your final version of this doesn't appear until the week after. That's not a big deal. But we do need to have it somewhat done or started or partly done for next Thursday. Okay. It's okay if you choose your own project. You can choose the same project someone else has done. I'm already seeing 2 people have chosen ArgoPy and 3 people have chosen PyMagic CC. Great, no problems at all. That's fine. Brad, your link doesn't look right. Let's see, I can go and I can fix it. That's fine. Oh, no. Whenever you see in documentation someone put brackets around that, what that's meaning is supposed to replace that this is the variable name and it replaces your whole name. So project topic is in angled brackets to be replaced with the whole name. And when you're doing links in Markdown, there's no space. So I'm just going to clean up this link and do a commit. All right, commit changes, so we're all on the same page and we're able to look at everybody's stuff. Anyways, so hopefully you're working on that. So I will ask that question. Is there anybody who needs to have a discussion on either the project in general or a specific project where you're like, it's not working for me, I'd love to talk about it?
I just edited the file, James, so hopefully mine should be there soon.
There you go. Thanks very much, Mike. Perfect.
No problem.
Here we go. Yeah, I'm now seeing you guys are doing this as you want. So I will confirm that merge. Okay. Now here's the trick. Oh, because you both added a line, we got to do some conflicts. Okay. So, but I can do that right here. Oh, so Emmanuel, see, you pushed before you polled. Okay, so there's a rule in GitHub: always poll before you push. My guess is you forked it a while ago and only pushed it now. No problem. I can update this and I can edit it myself. But that's how we resolve a Git merge, right? So I edited that file to make it work correctly for everybody. And I'm going to mark that merge as resolved. So I've handled the merge in terms of it. And now we can do the confirm. But now we can do the merge. Anyways, great. In Slack, someone says, I have doubt about my project PyMagic CC. Could you turn on your microphone and explain to me what your doubt is? As in you're unsure about choosing it, or you have a question about using it?
Hello.
Hello.
Hi, Professor. So my doubt is that a lot of examples like matplotlib plots are already given in the examples in that
Yes.
repo. So I'm not sure if I can come up with any new plots as such. Is it okay if I can reproduce some of those examples?
Yes, it is okay if you reproduce those examples. So let me just, okay, so I was trying to go, okay, so your README doesn't have a link to the paper or a link to anything about it, but I'm sure I can just go in and I'll do it this way. Let's take a look at all the projects and let's take a look at that and have a conversation. So you have chosen PyMagic. Okay, great. I want to go to the software repository. And there we go. There's the read the docs. Okay, so here is how to use it, right? So what we typically do is we run something, we run some model, right? So you have to run Magic CC, right? You have to actually do it. You have to call it and make it go. And then you load in the data. So it is totally appropriate to reproduce this plot, okay? But what I don't want you doing is just going to the Jupyter Notebook and being like, oh, that's all you do. You just you do this. Copy, paste. Okay, that would not be cool. That would be basically saying, here's my answer, right? Copy, paste. I'm going to ask that for the visualization, go ahead and look at this picture, even put a reference saying, my goal is to reproduce this, but think about this as being the answer. Okay, and don't just copy and paste that directly, but you could definitely take a look at that picture or the other picture and use that as a motivation. I think that makes a lot of sense. And moreover, the examples, right? Where did the example database?
There is one
Yeah.
notebook in the Git repo.
Yeah,
Yeah, this
notebooks,
one.
right? So this example, anything in here is really showing you how to run it and how to use it, right? So you're really just taking these and turning these into a workflow. But yeah, you definitely rework one of the plots or just do it on come up with a different way of making the same, plotting the same data, but in whatever way you'd like to do it. Regionally split and global scenarios. That's sort of cool. Yeah. Yeah, these are awesome. Any one of these ones. I said just copying and pasting the example and calling it that your own work. Remember that I can see this documentation too, right? So, okay. Just to double check, the last day of class participation would be next Thursday, right? Yes, next Thursday in this session. Like I'm recording these sessions, but next Thursday, the expectation is you're going to be able to be here because I want you to interact with each other about your projects. So Thursday, June the 17th is, I don't have a lecture. I'm not giving a talk, but call it presentation day. You're not really making a presentation. You're just doing similar to what I'm doing, which is showing people your GitHub repo, showing people your code, showing people your report, and they're going to go, hey, that makes sense to me. I'll remind you that one of the things that I'm going to try and do is test your workflow. Okay, and what that means is I'm going to go to your project and I'm going to try and run your workflow on a shared machine. So let's just I have too many windows. Which one is? Yes, those are all my repositories. Thanks very much, computer. I must have gone and jumped to something else. Fine, we'll just go back. GitHub, J-Monroe project. Okay. So if I pick one of these people, and Yashar, I'm going to pick you only because you're on the top of my list. What I'm going to do is I'm going to go to here and do what you tell me. Okay. So this is not actually a piece of instruction. You can assume who I'm running this, I have a conned installation. Okay. But this should be something that I can copy and paste to make go. So my question to you, Yashar, is this really the line that needs to be typed in? Is
Hello?
all of this necessary? Yep, Yashar, yep.
Yeah, sure. Well, now, in light of what you said, probably maybe I want to modify what I've done. This is just a short
I know.
history of what I've done, but now
Yeah.
that you're saying that you're gonna need to copy paste this as
Yeah, well,
such,
I'm going to try and follow your instructions as you've written them, right? And so just as a total minor thing, that capital M, that capital C, and that capital S, those won't work.
right.
Okay, so what I'm suggesting is you should test your own instructions.
Absolutely.
Okay, or and remember, there's a group of you, and you can see each other. You can see what you're doing. So this isn't an incentive to all choose the same project, but you always could get together and strike up a little conversation. I don't know if you can create channels. Like create a channel if you want, or just do it in general. You could say, hey, I see you're doing this as well. Can you follow my instructions? Does it work for you? Right? I'll check yours. That would be totally reasonable. Just don't. What I see sometimes is people take a README and they copy and paste the README from the project right in here. Especially when someone says, you can either type in conda install or type in pip install. Make a choice. Which one do you want me to do? Because I'm going to do whatever you tell me to do. Anyways, that's great. Okay, so we've had a couple questions on the project. I'm also okay just saying short lecture, go and work on the project if you want. But we are here and we have some time. So is there anything else about the project or its setup or particular?
Hello, Professor.
Yes.
Yeah, so in the instruction part of the project outline,
Okay.
so the first line tells develop a software code that computational solves a scientific problem. So I am a little bit confused about this statement. Can you clarify this? Like, do I need to develop a software?
No. So this is in the section called introduction.
Yeah.
Okay, so the sentence you need to read is in computational science broadly.
Okay. Oh, sorry, I missed
This is
that
what
part.
we do. Okay, we develop software codes to develop problems. Okay, and so what
Yeah.
I've done is I said step one, choose an existing software code that solves a scientific problem.
Yeah, I got it. And there is another question. Suppose I am finding it hard to identify the computational task in the software package.
Yep.
So can I get help from you? Like,
Well, that's an excellent question. So I'm going to ask you a question, which is, which package are you going to look at?
I haven't choose one yet,
Okay.
but I was just asking if I find it hard.
Well, okay. So what's the way of finding it, right? So we'll go.
Yeah.
Right. So we'll walk through this again. Okay. You got a list, right? So
Yeah.
so there are 24 different options, and the first thing I would do is I would just pick something that strikes your interest. Okay. If you might say,
I
hey,
think a Python library for Argosian data analysis. Number
so
8.
what's the ArgoPy? Why do you guys all like ArgoPy? You already had a lab assignment, like a lab assignment on it.
I'm just asking.
Oh, okay. So it just a few other people have chosen ArgoPy as well, and you already know about that one. We did it in the assignment. It's sort of
I was just I selected
no, that's cool. That's cool. but okay, so we go to the project, right? And what we're trying to find is the actual GitHub page for the software. On all of these software, if you're lucky, there's a link right here to read the docs. If not, if you read their README, somewhere in here, there'll be a link to the documentation, okay? Now, and I don't just mean the little example here like in the README. There will almost always be some reference to where the documentation is, okay? So here we go, documentation, read the documentation. Okay, and the documentation, okay, to be clear, is part of the package. It's just what's inside docs. This subdirectory, and every one of these projects has a docs. This is the exact same content that is on read to the docs. Okay, and it doesn't matter for which project, they all got it. They've all got a little explanation about what the project does. And of course, the paper would have that same explanation. And what I would start with is start with the usage, okay? And just see if you can get it to run, okay? That's the first barrier. If it takes you more than about 30 minutes to get it to do the first thing, you may have information technology skills which are not sufficient. There may be enough about downloading, installing packages. It should take some effort, okay? If it takes a few minutes, that's okay. But you shouldn't be struggling for a full day trying to get the simple example to work. If you follow their README and you do this, something should appear. Okay, and if it appears, you're like, oh, okay, that's cool. I got it to work. Now you're up to the point of what I want to do with it. And this is where we look through the user guide. Okay, user guide, example notebooks, whatever it's called. Okay, and what I would do is I would start reading the documentation. You're like, okay, so what does this package do? What's the thing in science that it does? Well, what it does is it fetches Argo data. This is actually a package which communicates with Argo Viz, which is a piece of software I was talking a moment ago. So effectively what it does is it loads data. It loads data in different regions. Okay, it sucks out data for one or more floats, and it understands where that data comes from. So the computational task here is downloading the data, right? So you might just say, okay, I want data from the North Atlantic for last summer.
Okay.
And okay, great, I have the data. Well, that's a computational task, getting the data. And then you might say, okay, I've got a bunch of data. Let me take the average of it and come up with the average temperature per latitude, or average temperature per month, or whatever you like. And if you have no idea on what's appropriate questions to ask, okay, manipulating data, right? Or I would do is I would actually go down to visualization, right? Here are some of the things that we typically visualize: locations of plots, right? Where plots are. But for Argo data, we also could look at profiles, right? We look at how the data changes with depth, or we may want to look at what averages or means of a whole bunch of data is together. So you could use the user guide to sort of say, just to investigate what kinds of things can you do with this data, get some data, right? Because this is a package which is designed to download data, and then make some plots of stuff. And what is the stuff? It's usually temperature and salt content and pressure as a function of time or space for this package. But you may not choose to do ArgoPy because you're like, I don't care about little things floating in the ocean. I think that, and this is where you got to go and pick something. What's cool to you, right? And,
yeah,
and
let me have a look.
that's the work, right? So in terms of going through it all the way through.
Yeah,
Right?
Professor, I got it.
Yeah. Okay. So you choose something and you're just putting it together as a package. It's got to do some computational tasks. There are 2 computational tasks, and remember that it's not really about the package. Okay. What am I really evaluating? I'm evaluating whether or not you're able to use command line based tools. Are you able to program Python at all, right? Load data in, save data, make a loop, do something. Are you able to use a Makefile? Are you able to make a plot? Are you able to use data structures or data file formats? Could be pandas, could be something else. There might be another library that you choose to use, but you're able to put these things together. I'm trying to see whether or not you actually could do this in a domain of science, so that when you go and apply this to a new domain of science, you're like, okay, I know how the pieces are supposed to fit together. That's my intent.
Yeah, Professor, thank you so much.
Okay,
Got
no
it.
problem. So I'm just trying to get a sense of the class. I'm not seeing any comments, but I also don't want to shortchange you. Is it best if I just give you time to go work on the project right now and say good enough for class today? No one has their camera on, so I can't get any, like, there's no thumbs up. Mike says thumbs up. Okay, Mike, on behalf of the class, I accept your recommendation. And we will see you on Monday. On Monday, we'll take up assignment number 8. And I've got a little bit of content on working with big data and how we begin to deal things that I want to talk about, but that's where we're at. So have a great weekend, everybody, and we'll talk to you later.